this seminar series. It has been very interesting to me and hopefully to others. All these presentations, they were very exciting and interesting. So what I would like to talk about is what I call the capacity of discrete time as stable stochastic dynamical systems. And then I would try to show some interaction between control estimation and information transmission. Okay, so the outline of this presentation is basically, I'm missing something here, I cannot see it. Okay, I'll put it up in the corner. I would go back to the Shannon definition and then notice that it can be used for signaling and control at the same time without much generalizations. And then discuss the issue of control and coding. Then I will discuss some motivations. If I have time, I establish some dualities between stochastic control and information theoretic definitions of capacity. I will discuss some application examples. I picked some Gaussian examples. Then I will discuss some communication examples, and then I will conclude. So basically, the Shannon's figure is based on, we have a channel, which I call a decision model or a control system. So Shannon's model of communication is to introduce an encoder, and then there is a decoder, and of course, some messages that are randomly generated. And these messages are uniformly distributed. So depending on the information available to the encoder, you generate the coding strategies. Of course, the input to the channel, I call it a control process because it's by analogy the same thing. And then the output to the channel is this yi. A channel or a control system, it has some conditional distribution. So here I picked one that it says the current output at time I depends on the previous outputs up to time I minus 1. And all the past inputs ai. Of course, there is a decoder, is Shannon's model, and then one defines the probability of error of decoding W by W hat, and one wishes to have a coding rate which is as maximum as possible when the block length is sufficiently large. That means to find the supremum of all achievable rates for which there exists an encoder and a decoder. This is the classical problem of Shannon. If you notice here, I just replaced this encoded part. Do you see my my cursor, right? Yeah?
I can see it perfectly.
Yeah, so basically what I did here, I replaced this encoded part and I called it a randomized strategy or controller encoder. And then I break it into two parts, a part that is responsible for stabilization and the other part which is responsible for information transmission. I will come back to this. It can be more general, but this is a simple presentation. So the main activity which we have been following for the last 5 years on this area is to talk about what is the control coding capacity. That means their capacity of control systems which can be stable and unstable. So in this definition, the name doesn't really changes the situation that we are dealing with a dynamical system. This can be a channel or a control system. The only difference is because I use the word control strategies, these strategies have a dual role. They try to control the output signals and encode information. So basically, if you use this definition in the classical control theory, then that means control systems act as communication channels to signal information from one processor to another processor, with the aid, of course, of encoders and decoders. So the difference between Shannon's coding capacity is that sometimes you need also the controller part of the encoder. And without the controller, you will not even have achievable rates. So we want to develop first, I would take some classical stochastic control problems, and then I would take some classical communication channels, which can be stable and unstable, and then see where it will lead us. Some of the conclusions that are expected here is that for control systems, there will be a minimum cost to control the system into stability before you have any coding rate. For communication systems, for some communication systems, it would be the case that stable channels or poles result in increased achievable rates at no expense of transmit power. Okay, so let me start with the methodology. First, there is an analogy between Shannon's information transmission and stochastic control with randomized strategies. So in other words, channel input, channel outputs are analogous to control processes. Inputs are the A's, outputs are the Y's. Channel distributions are conditional distributions. Control system distributions are also conditional distributions. Now, with respect to controllers and encoders, one way to link them is to replace all deterministic control strategies by randomized strategies. And UI serves as a randomization. So in stochastic control, one is given such a model, and then one wishes to optimize a certain pair. Now, in information transmission, you also need to achieve a certain coding rate. So this is the fundamental difference. I should say there are two fundamental differences. There is also a hidden decentralized feature if you do information transmission as well as control, because you have actually two strategies. You have a controller encoder strategy, and you have a decoder. And these share different information. The decoder doesn't observe the message, but the encoder does. So this feature, although it's not apparent sometimes, in real applications, when you try to solve specific problems, it comes out. So what are the elements of establishing a converse and a direct control coding theory? I'll just do some review of this. So if I call the encoder the controller encoder, so that means controller encoder strategies map messages into control actions. And usually there is a power associated with the transmission cost at the transmitter. Oh, this power, of course, is the payoff of control if somebody was doing simply control. Now, in information transmission, one usually doesn't want to deal with maximizing or finding the capacity, the supremum of all achievable rates by using encoders. So one uses randomized strategies, and one attempts to show that capacity is actually independent of the messages. And this is the set of randomized strategies, I would call, which are conditional distributions. In this setup, basically, I assume that there is noiseless feedback, not noisy, noiseless feedback. Of course, if there is no feedback, that means this Y will not be part of the definition of the controller encoder strategies. So two information measures that appear in the converse coding theorem is the mutual information between the messages and the outputs under a given coding strategy, which is well known, is the logarithm of the random nickel time derivative between the sequence yn, condition on the message, and the output distribution of yn. This basically can be written as in a sequential form where this AI are these encoders. Another important measure which comes up is the directory formation from one process, from one sequence to another. And this directory formation was coined by Massey, and it's due to Markov, who introduced it in 1973. Once Massey introduced it, then Kramer did a PhD thesis on it, where he showed how this measure is important for feedback, or whenever you have feedback between one process to another process. So now the standard converse codec theorem says the following. If you want to find what is the operational achievable rate, which means to determine an information theoretic definition of capacity, then there are there are two theorems one tries to prove. The first one is a converse codec theorem, who says, suppose there exists a controller, encoder, and decoder sequence with probability of error that asymptotically goes to 0. Then the rate is less than or equal to a limit infimum supremum overall encoder strategies of the information measure I introduced earlier. But then since these inputs are specifically generated using this randomization W, which is uniformly distributed over the messages, then one has this upper bound over all randomized strategies. So no longer one needs to take such encoded controller strategies. And this gives you an upper bound. Now, of course, there are certain technical issues one has to be careful with this. Is the issue of existence of the supremums. There is, since you are doing supremum, one needs upper semi-continuity, but then mutual formation is lower semi-continuous, so one needs to prove also continuity. There are issues of convexity, existence of asymptotic limit, and this part here that I put in red. I put this in red because you can define this quantity, and this quantity, even if you take the limit and you have a limit to exist, asymptotic limit, you still can be a function of the initial distribution. So there is the issue of whether you want to define your rate to be independent of the initial distributions of your channel or your control systems, etc. These are well known. Then comes the direct codec theorem. So once, let's say somebody identified this measure, which is straightforward, this is Fanos inequality, then one tries to prove achievability, basically to show that the supremum of all achievable rates is this quantity identified in the converse. And there are at least 3 different approaches to do it. One approach is to show joint asymptotic stationarity and ergodicity of the joint process of the input and the output. Another approach is to prove Dubrush's directory formation stability, which means the information density converges in probability to this quantity. And of course, also the average payoff is also stable in the same sense. And in order to prove achievability, you also need to have continuity of this quantity with respect to the power. Anyway, for 2 and 3, you still, one wishes to obtain achievable rates, which are again independent of the initial conditions. So these 2 does not guarantee you. I omitted to say Gallagher's exponents. Gallagher's exponents, basically, one tries to show that you have achievability by computing the error exponents. Of course, Gallagher goes at length in his book by analyzing what does it mean the encoder knows initial state, what does it mean that the decoder knows the initial states, and so forth. And of course, if you ask that the encoder is insensitive of the initial states and the decoder, this is equivalent to what is called compound capacity. So it's more conservative than if you do not. So, okay, additional problems that come up if somebody is given a specific system is, okay, how do you compute it? If suppose the converse, you are able to arrive at this point, which is easier, the standard approach that I like is first, before I go and prove the direct part, I like to first determine the information structures given a specific model and payoff, because this will simplify things. So this has to do with the information structures of randomized strategies. Okay, and then if you have this, then it makes your life easier because you can bring the problem down to a Markov decision, and then you can attack it using this approach A, B, and C with respect to the direct and also the converse, because you have to take the per unit time limit. And there are issues of computing the capacity of randomized strategies. So this is problem one. Problem two, of course, is the most challenging one, which is assuming that you prove this is the capacity, then how do you construct encoders and decoders to achieve it or to operate below it suboptimally? This is still, this problem is still open to this day. Okay, so now why I was interested in dealing with unstable systems. I remember Nicola earlier mentioned the last time, he says, why would somebody would be interested in nonlinear systems? Well, in control system applications, I was motivated by the fact that control strategies, sometimes it's important to signal information that you encode in control strategies. This is important in cooperation in multi-agent systems. Some people who do robotics, they call this implicit communication. Basically, you encode information in the control strategy of one robot. There is another robot that observes the output behavior of the first robot. And based on the movements, it tries to decode what it's trying to tell him. This is called implicit communication. Okay, Savas Loizu, he actually did some simulations. It seems to work on this. We are in a joint project funded by the Cyprus Research Promotion Foundation. But he's looking into doing the actual experiment. Of course, there are issues of monitoring of failures of actuators. Now I must say that signaling economics is very well developed at some level with respect to financial markets, contract theory, to deal with asymmetry of information. And the person who brought it up was Michael Spence. Of course, in biology, I have some experience with control of gene regulatory networks. So I found this to be of interest if somebody wishes to suppress certain genes by also applying signaling elsewhere. Now, this is as far as the control system applications are concerned in economics and biology. Now, what about communication systems? Communication systems, some recent work is concerned with energy harvesting. Energy harvesting often requires control. You have to control the channel output to have a minimum energy harvest. So this is also part of the problem of control. So that means the encoder here has to be contain a control part. Of course, under general framework, one can say, well, design encoders with control capabilities, whatever that might mean. So let's see what the examples will give us. Okay, so before I do this, I will skip this. This is basically, I was thinking to give you some idea how a dual problem to the problem of control coding capacity, you can define the cost rate where you minimize a cost subject to a rate constraint. And here, basically, if you are a FIMO over randomized strategies, then if you remove the rate constraint, you have a lower bound. And then if you use deterministic strategies and you have classical information patterns, that means you cannot declare a better payoff between this part and this part. So you're back to the control part. This tells me basically that if I have a system that I'm also controlling, there should be a minimum cost of control before power can be turned into information transmission. And this comes from this, this simple result. I will come to this. Okay, let me skip this. Basically, the most important part is the part about this decomposition. If somebody tries to solve the original problem, it turns out that sometimes, depending on your model, the optimal randomized strategy consists of three parts: control, estimation, information transmission, and sometimes there is a specific order how one computes each one of these strategies, which is closely related to person-by-person optimality of decentralized strategies. So let me go to a specific model. One of the things that I consider is consider in general control system. I assume an initial state. If there is an initial state, if there is not, then S will not be here. But anyway, suppose I have a model that depends on finite passed on the previous outputs, finite passed on the previous inputs, the initial state, and then I have a payoff that is consistent with that, but a different memory on this. For example, this can be the output could be like a nonlinear system like this, where WIs are independent processes, independent of S. First, from the converse, since the converse will hold, we need to go one step further to identify the information structure. So basically what I'm saying is this. You know that any radar is below this. So before you go and take the limit, then it is better to concentrate on this quantity, given your model, and try to understand what is the property of the maximizing distributions. So this is basically what I'm doing here. So to understand the difficulty here, I'm bringing to your attention that this is the quantity that we take the expectations subject to the power constraints. But this quantity involves the channel or the control system distribution and involves the output distribution given the previous outputs and the initial state. And this is now a functional of the input randomized strategies, these quantities here. So even if I take expectation of this quantity and I don't have any power constraints, let's say I was doing a finite state Markov decision problem, then we have a nonlinear functional of this quantity here. So it's not very clear how one can use Markov decision theory to determine the information structures. So here is what we use, what is called variational inequalities in these references to determine how we can actually determine information structures. So let me give you the first theorem, which I call it a problem with fully observable control system. Suppose my model here does not have any path dependence on this, and neither does this. So n equals 0, L equals 0. This case here tells me that the optimal randomized strategies would only depend on the previous outputs, which is I minus I. I is the maximum memory of my payoff or on my control system model. So basically, you come up with this characterization. The fact that you know this is the information structure simplifies considerably your model. But another thing that comes up is no filtering is involved if you try to optimize this quantity. It's only control and information transmission. So let me, before I give an example, let me give also another information structure for partially observed. Suppose now we have path dependence on the previous output, as previous outputs and previous inputs. Then these previous inputs basically form the state of the encoder. So in this case, we have this quantity here, the channel is this, we have this quantity here, but then this quantity is a functional of this distribution and the filtering of this quantity over the previous outputs. This is a case where it would involve filtering, control, and information transmission. I will come back to this with some examples. So let me start with the very first simplest, fully observable stochastic control system. So here I took the output depends on the previous output, the current input, the noise is IID Gaussian. It doesn't have to be IID, independent is enough. This is the initial state. I took a quadratic cost, the standard assumptions of a linear quadratic theory. Then by maximum entropy principle, we know that the joint process Y and A are actually jointly Gaussian. Because this is Markov now, then we have a Markov conditional distribution. And then because of the Gaussianity, the optimal input, it has two parts. One is the control part, the other one is the innovation part. The control part is a linear function of the previous outputs with some scaling that needs to be determined. And then we have the innovation part, which is actually Gaussian independent and independent of the noise. And then the output is this. So here it comes now that in order to go further and talk about the asymptotic behavior of the rate, then of course this gamma has to be such that this quantity here has to be stabilizing. So meaning uniformly stabilizing if you allow your coefficients to be time-varying. Anyway, the optimization problem comes up to be, it's a log determinant problem. It involves this innovation part, but not the control part. And this is because of the nature of the strategies. And then the power constraint, one is needs to determine the optimal strategy, control strategy U, and this innovation covariance subject to the constraints. Now, because this guy does not depend on the control, this problem is equivalent to minimizing over U first, and you will come up with the optimal U. That is precisely the optimal strategy of the linear quadratic Gaussian fully observed problem, where you have your gain, and then you have a control Ricard equation, which is the classical control Ricard equation of stochastic control of linear quadratic Gaussian problems with full information. Of course, now I just work out the scalar here to see what is the information transmission. If you once you compute this quantity, then you substitute you can substitute it here, and then you take the supremum, and this would involve some kind of water filling in time. I'm doing the scalar case, so there will not be water filling space. This is how the optimal covariance matrices are computed. This is a Lagrange multiplier. And then you have the information control coding capacity for finite Ni. It involves these terms. Now you can notice that this it involves n different versions of this CI, which is the right-hand side of this. And of course, this is greater than 0, provided your gap pi you allocate is above a certain minimum value for each I. Okay, so now the next question is to see what happens to the rate. But to go further to talk about the rate and to investigate LND and E, and you take the asymptotic limit, okay, you need some detectability, stabilizability. So now, because I know my friend Yüksel will ask me this, in this work and in our published work, we actually took a lower bound on the capacity by interchanging the limit and the supreme over these strategies. Okay, so to do that, in order to have convergence, we need the standard detectability, stabilizability, and then it comes up, we have capacity, provided the power is above a certain minimum power.
Vamos,
then, yes.
Make it to help also our audience digest this, lots of rich results, wonderful results. I just want to maybe emphasize one attribute. So here you are solving the infinite dimensional problem, right? Not the single shot infinite horizon problem.
The sequential is this. This is the sequential at each instant of time. Right. And because it's scalar, so and
what I mean is that what I mean is that you are solving the information theoretic formulation where basically you have a block version of.
I'm not doing the block because I turned the problem into sequential. It is sequential. The problem is sequential.
So when you do the water filling, how does
the water filling? It comes from this. This is the finite Ni, yeah. Mm-hmm. So this is the optimization, but this guy here doesn't depend on the U. It depends only on the KZ. So basically, once you get this solution to the control part, then you substitute it in the average cost, and then you optimize this subject to whatever this payoff is. So this kind you can solve even for finite Ni for the scalar case. For the vector case, is more involved. We found how this would be done using water filling in space, but I did not include it. I don't think.
But for the vector case, then my knowledge tells me that for the vector case, it's not always the case that the optimal encoder is linear.
No, because this is optimal. This is the answer. Mm-hmm. So this is the vector now. This is determinant. So the fact that it's linear is because, I will tell you why it's linear. The fact that it's linear is because this problem, if you write down this quantity here, which is basically the finite Ni, it's just the entropy of the output minus the entropy of the noise. The joint entropy of the output.
I'm trying to understand the formulation. So anyway, your formulation is the information theoretic relaxation of the Gaussian signaling problem, or is it the actual capacity?
No. This is the capacity. This is I'm working on the capacity. So basically, I'm doing this now. Okay.
Okay.
I'm computing this quantity, and
Mhm.
because I have the case where I have a Markov here,
Mhm.
so I here for me is 1.
Thank you very much.
Okay.
This clarifies it.
K is 1. So then, because this quantity collapses into the entropy, the enjoying entropy of Y minus the enjoying entropy of the noise.
Thank you very much.
So you know that from the maximum entropy principle, join the Gaussian maximizes. So that's why you end up having this quantity here, that here you have a linear. And this I took up.
And one final question is, when you go from finite limit to infinite limit, can you explain how do you establish the optimality of a stationary process?
Okay. I will discuss this in a minute. Okay. So this is for finite. I like to do these things for finite. So all this is for finite. Basically, this collapses to, because of the information structure, you have only dependent on the previous one. So this quantity is basically the entropy of the whole sequence of Y up to time n minus the entropy of the noise. This is easy. That's why it comes up of this form. The denominator is basically the entropy it's related to the entropy of the noise because the noise is independent. So this is if one wants to solve it finitely, this quantity. It has not yet, we haven't given a meaning in terms of achievable rate yet, okay? In order to give a meaning in terms of achievable rate, we have to take 1 over n, okay? We have to show that this limit converges, and then we have to go through ergodic theory. Either we have to prove joint ergodicity, formation stability, the things I talked before. For this specific example, okay, we gave here the finite need, but then, as I said to you before, in the paper, in the information theory paper 218, we took a lower bound. We did not address the limit supreme. We said limit supremum is a lower bound by taking first the limit and then by taking first the limit and then the supreme. So we gave a lower bound. And this lower bound is given by this quantity. So I haven't proved lim sup is equal to sup lim, okay? I will discuss this point. So if you do this and you take a lower bound on the rate, then of course under detectability, stabilizability, you have convergence, and then you have ergodicity, and you have the enjoying input-output process. Then you can prove you have ergodicity, formation stability, and then from there on you get achievability. Is it clear now? Yeah, is it clear?
Thank you.
Yeah. Now the question about at that time when we did it, we didn't pay attention to trying to prove this limit supreme. And they interchange. So we got a lower bound, which is achievable. Now here is where Gautami comes, and he did something which is using convexity. Okay, but I will return to that in a little bit. Okay. So what this thing gives us is that an achievable rate is given by this quantity, where this quantity is the solution of this optimization problem. So this is the asymptotic problem. So the difference between the stochastic control problem and this problem is that you also have this extra term here, which has to do with rate. The stabilizing controller is this, and this is your Ricard equation, and that's why you need to have detectability, stabilizability, so that you have a unique stabilizing non-negative solution to this Ricard equation. Now, the other thing is if you go and you replace KZ, the information transmission part 0, then capacity is 0, but G is stabilizing. Your controller is stabilizing. And then this is the part I was saying, once this is 0, then this solution here collapses to the LQG optimal control problem, the optimal value, which is the cost of control to have ergodicity, basically, under these conditions. And this is classical. Now, if you go and say, let me compute some special cases, which we do here, some scalar cases of this quantity, you again see that you need a minimum cost to control the system into ergodicity before you can transmit any data. So that's that specific case. And this is when your C is unstable. If your C is stable, one can verify that that model I gave you tells you that feedback does not increase capacity. If C is stable, basically it tells you, if I go back to this, then you have asymptotic stationarity. And then if you do the water filling formula, then you can verify that feedback doesn't increase capacity for stable. It's only for unstable, for this model. Now, this thing here tells me for unstable pole, the C here is the pole, okay? This is how capacity is. You have to actually, this guy has to be, where K mean is the cost of control. This is the cost of control to drive the system into the asymptotic stability. And then you have a rate loss of a stable system versus stable systems. And these figures here show that, okay, if you have an unstable control system, if you use no feedback, there's nothing you can do because you cannot stabilize the system. If you have for a stable C, then it tells you once you are above a certain K mean, which is this point here, this is the case for C equals 1.5, then you have capacity. So this is the case here, the same graphs, but for a different parameter values, okay? So for a stable, you always have this cost of control before you can have any rate to be transmitted. Okay, so I'm done with this. This confirms basically reproduces existing results of classical linear quadratic Gaussian, but for fully observed. Now, what happens for partially observed? I took two more models for partially observed. We took, I should say. We took this one because people in communication systems, they like things that they depend on previous inputs and the noise to have memory. So here, this is a multidimensional version. Well, here says the noise is Markov. Here it means it has interference, intersymbol interference. I also took initial state. Again, the cause is actually quadratic again. Okay, the assumption is that the noise is independent of the message. Okay, this noise is independent of the message. That's what that means. Now, when one looks at this, from the converse again, you have to solve this optimization problem. Again, now it comes out that this AI is a state that is known to the encoder. Of course, the encoder knows all the previous inputs and all the previous outputs. But the decoder doesn't know it. And because of this, you have a different now strategy for this problem. Now it would involve filtering. Again, if you go through the maximum entropy principle, because again, if you try to compute this from the converse, it would be the entropy rate of y given the initial state, the entropy of the sequence of y of length n minus the entropy of the noise again. So again, if all of them your V's are Gaussian, which here W is Gaussian, and the initial states are Gaussian, then maximum entropy kicks in. Again, you have your optimal randomized strategy. Now it would be a function of the previous y. The coder knows the initial state, and because your channel is Markov and my payoff does not depend on previous inputs, then it will be a function of all the previous y's, the previous a, the previous noise, and this independent process, which is linear in this case. So UI is actually, again, the control. This is the part that depends on the previous input, okay? This is the previous noise, and this is the independent process. It's an innovation process. But then one can realize that since this guy and this guy is the state of the input, then you can put this together. The state is known to the controller encoder, but is not known to the decoder. So basically, you can turn this input here to, instead of being a function of all the previous outputs, you can make it to be a function of the previous output yi minus 1 and the conditional estimate of the state. The reason is because you are conditional of this and this, your channel is again Markov, but you need to condition on this too. Okay.
Almost can I ask a quick question?
Yeah.
So when your input also depends on the previous input, when your output, could you explain again the argument for optimality? Because just maximizing the entropy is not sufficient. There's also
yes, because you see, the thing is, for this model, this V, okay, satisfies this condition here. You see this? So because of this, then if you write down what is the information measure of the converse, is the entropy of the sequence y minus the entropy of the sequence v. And because you have a quadratic payoff, then again, you fall into the maximum entropy principle of continuous random variables, okay? So there's no loss of generality to take enjoying process A and Y and V, which are jointly Gaussian. This is a standard thing, okay? That's why it comes out here too. This quantity has to do with the entropy of the sequence Y, and this has to do with the entropy of the sequence of the noise V. The thing is, here now there are multiple strategies, and now, okay, so one can try to compute each one separately, but it turns out that one needs to identify a sufficient statistic. You need to identify the state of the controller encoder, which is known to the controller encoder, but is not known to the decoder. So this part here, which uses parts outputs, basically would be consist of two strategies, gamma 1, gamma 2, and this is the conditional. Of course, there is another strategy here, there is another strategy here. So there are 4 strategies actually. Okay, so for this problem, the information measure at the converse is actually the directed information between this sequence, the previous noises to the output sequence, and it breaks down to these two. I don't know why I put this. I think this should be removed. It's the same thing. I think I wanted to put here that this is the innovations process, but I will come to this. Now let me see if I can capture, I can reconstruct some of the known stuff which are done by others in information theory. A special case of this is if I have no previous Ys, V is IID, so I have only intersymbol interference. It turns out this is a finite impulse response model. Power constraint is this. It turns out that when you compute this quantity here, this quantity involves two Ricard equations, but then it collapses down to involving only the Ricard equation of this error covariance here, which is the encoder is actually sending there. Another example is to take a Gaussian model, okay, and you take the V to be autoregressive unit memory noise, basically this. Again, this comes out to be exactly the same strategy, and it's simple to see why this is consistent with this, because VI minus 1 is YI minus 1 minus AI minus 1, and you're taking conditional, so the Y is cancelled, okay? So in this specific applications, there is no control. It's only estimation and information transmission. Estimation because the encoder needs to estimate sense there, basically. Now, this is where things become interesting. If I take the asymptotic infinite horizon problem, not trying to solve the limit and maximum for these problems. I take a lower bound on the rate, and then I impose detectability, stabilizability. And of course, these conditions now, one needs to be careful, because detectability, stabilizability, you have a case where if you substitute this VI in there, that means you get a state and an output, and the noises are correlated. So you get into generalized Ricard equations. They have this extra term. So this classical detectability, stabilizability are not enough. So you need to go to the generalized Ricard equations. Peter Kane's book on linear stochastic systems does a thorough investigation of this. Anyway, if I solve the asymptotic limit, then we notice three things. If C is unstable, and I'm talking about the AR1 noise now. If C is unstable, the feedback increases capacity, but I have a minimum power. What it tells me here tells me that feedback capacity increases with the instability C. I will show a figure now. If kappa is less than this kappa mean, it tells me there is no solution to this optimization problem. So in this case, it means there is no time invariant strategy that gives me the achievable rate. So I have no choice. I need to seek non-feedback strategies. It turns out there are non-feedback strategies for this regime. And also for the other case when C is stable, for any case, for any power, again, for this regime, there are no time invariant strategies that have a solution to my optimization. The feasible set is empty, in other words. Anyway, so what do we show? We show that, okay, since for regimes 2 and 3, there is no feedback with respect to time invariant strategies, we wanted to see whether there is non-feedback strategy which is achievable. And we just picked IID input. IID input turns out to be to generate things which are asymptotically ergodic, and then we have a rate. Okay, so let me see some plots here. What the plots say that if I'm using time invariant strategies, it tells me the following thing. This blue line here is the capacity of this channel if I have no memory. So it's the memory. The next level up, this guy here, is when I invoke IID input. And the reason I said is because I want to achieve a lower bound. The next level up is again when I use IID input. And here it comes now. The point that C is 1.5. So above this point, I have feedback. Below this point, below this point, there is no feedback. This is the IID input here. So it's suboptimal. And the same thing as here. This curve here is when C equals 2.5. Okay, this is the 2.5 curve. And below this is the IID input. These are the three regimes because I have feedback only if I'm in regime 1. What this tells me now, it tells me that the more unstable the pole is, which is basically this for this channel here, the more unstable it is, the higher the rate. Okay, I interpreted that in very simple terms. If the noise is more unstable, that means the more unstable it is, the more predictable it becomes. So the more predictable it becomes, the higher the rate. And this is what this curve shows. Now, I have another curve, which is a little bit contradicting with some of the other work that people have done. I compare what we got in this specific application with AR1 noise to Kim's 2010 IT paper. And of course, Young, Gavzil, and Darigonda did something in 2007 that Kim revisited. And then Batman's lower bound that he applied linear coding scheme to find a lower bound that then Kim came to show this is actually the feedback capacity. It is not valid for me to compare our results because these guys, they derive feedback capacities or achievable rates for stable, but I'm doing a stable. But I wanted to compare basically whether their formulas, if applied to a stable, can do well, or at least as close as to what we get. Surprisingly, it is not so. Here we have the lower curve is the achievable rate of stable IID input, non-feedback. This blue curve here is Kim's feedback capacity for pole at 0.5, okay? And the next level up is this one. This is for C equals 2. And here we are up here. If we use achievable rate for a stable, the IID input, which is a lower bound, so we will have this green curve, and the yellow is the feedback for regime 1 because we have feedback capacity. Of course, there is a lot of activity around here at low power, which although you see here that as power increases, IID input and feedback capacity for stable given in the previous work gets closer and closer together. At low power, it does not, okay? So this actually says to us that previous developed formulas for stable doesn't work for a stable. That was a big surprise. There is an explanation for that. I will return to that. It's almost like contradicting because their method doesn't rely whether to derive the feedback capacity, does not rely on whether the pole is stable or unstable. I think what, from what we found is basically is the choice of optimal input and the conditions imposed that gives us a different us, because we want detectability and stabilizability. And stabilizability is not imposed in their work. Okay, so let me move to this partially observed. Okay, this was the most general partially observed. We have a state, A is the control input. This is the partially observed state space model. I will not go into this, but even for this one can actually compute at least to show that Gaussian strategies are optimal. This is much easier because you only have a state, one guy, X. So here is basically you have a control and the information transmission part. Again, as I was saying before, in this specific example, you have the entropy of the output, but the entropy of the output given the previous output and the inputs. Anyway, here you end up identifying two Ricard equations and one control Ricard equation. I will not mention them. Basically, you have three Ricard equations for finite n. One is for estimating the state if the input is 0. The other one is estimating the input if A is non-zero. Two Ricard equations, and then, of course, you have a control Ricard. And then, of course, you have to optimize this quantity, which hopefully with the work of some recent work that turned this problem into convex optimization problems, hopefully would be one can be able to solve these problems. I don't know. There is another application we did where we have two systems in cascade, and we wanted to see whether we can encode for control system the output into a control strategy, use control system 2 to transmit information, decode, and then control system 1. Anyway, this is done. Okay, so let me go back to this problem now and I will conclude. This is the classical problem that many people worked on in communications. There are two directions. One direction in the 1970s has to do with coding schemes to give lower bounds, and another one is to give the capacity. Now, the surprising thing to us is this simple thing that the coding scheme of Badman's strategy that is used throughout, highly cited, also used by Wolffish. Basically, Badman gave a lower bound of feedback capacity by using a linear strategy of sending the error, of encoding a Gaussian message. Here, this is AR1, and he took C to be stable. Now, Badman derived his strategy by assuming at each n, average power is kappa. He turned the problem into some equation for this quantity here, which is the absolute value, because he used this kind of strategy that maximizes the signal to noise ratio. The sign of Gini is minus the sign C Gini minus 1. And this leads to this recursion. And of course, he assumed this thing converges, which it does basically, to this equation. And this is the equation that is given by others as the capacity when the noise is stable. That's the one I compare. Now, the surprising thing with this is that by the ratio limit theorem, it tells you that this ratio, if this ratio is greater than 1, which is required in Badman's lower bound, that means the absolute value of the gains go to infinity. If it's less than 1, capacity is 0. So basically, Badman's strategy, which does this, it means that if you use such a strategy, this thing will go to infinity. So you cannot use it. Not only you cannot use it, but if there is an epsilon noise in the error, because you multiply by G, which absolute value goes to infinity, then you will not meet this constraint. Okay, so we did such simulations without using this strategy here. It seems like it does better if you don't use it. We basically went back, re-derived, but we did not use that specific relationship. And it turns out that even for n equals 10, it gives better than Batman's strategy for n equals 20. We cannot solve more than n equals 10 because this problem was solved in MATLAB, and MATLAB collapses because the G go to infinity. So this is the new thing we discovered, that this kind of strategies are fragile because the gains go to infinity. Here is the strategy that is used by Kim in his paper to re-derive Batman's lower bound and to show is the feedback capacity. The peculiar thing about this strategy is using a time-varying strategy. At time 1, he sends a random variable, but then the rest of the times there's nothing sent. So in his case, X will not go to infinity, of course. He doesn't have that issue because of this. But in our work, it turns out that if the encoder knows the initial state, then such strategies will be sensitive, or will be sensitive to initial distributions of V1. That means there are not ergodic rates. There are different rates that depends on the initial state, but it's not the ergodic rate. And this is the one that we compare in the figures I show you. For stable, it does better than IID input, which we gave as a lower bound. We use time varying. They use this kind of time varying. Anyway, I think the next guy who actually understood something is not consistent about this paper is Gatami. He treated the Cover-and-Bombard general problem, which is the problem of additive Gaussian noise channel with general jointly Gaussian sequence subject to this constraint. I mean, if somebody reads his paper, it's very clear that he discusses some of the problems. This is the problem that is cited by many authors. Cover-and-Bombard characterize the optimal input Gaussian, depending on past noise and noise which is jointly Gaussian, and then gave a formula, but it's impossible to compute because one has to do this in blocks. We revisited this. Basically, what we did is we didn't like these blocks. So we went here and we said, well, a simple redefinition using defining Z to be the innovations. Well, it's not the innovations, the process of Cover-and-Bombard. If you do this, then you can turn this into a strategy that is driven by independent process, and then you have a sequential version that involves two innovations. One is the innovation of the output, and the other one is the innovation of the noise. If you go one step further and you use a noise as a state space, then these things become simpler. Basically, the state of the noise is this guy and this guy. And the optimal input, although we use a different method, is basically the same one that it was pointed out by Katami in his 2019 paper for stable noise. Okay, so there are two covariances, two innovation processes. And then we ask, okay, but if the input is like this, how can it be that Kim's paper depends on the state? Kim gave his input to depend on the state. So in this means that because the state is not available, it means that what is available is V. So it means that the optimal input, because it's additive here, is equal to this. But then in order to make this to be depend on the state, then one needs to know the initial state, and then one needs to be able to uniquely define S from the noise sequence and the initial state. Of course, this would be correct provided the state is estimated with zero error prior to transmission. Okay, but if it's estimated with zero error, that means one has to take a different look at this. I think with this I conclude. Basically, what we wanted to do is wanted to see whether we can generalize Shannon's coding capacity to have simultaneous control and information transmission for a stable control systems and stable communication channels. Okay, so basically, randomized strategies have the new elements, which they have a control and signaling part. We have also done some Markov decision problems with finite state space. Okay, so the last part, which I put in red, it says that whether such operational definitions for control systems will lead to new design methodologies and application remains to be seen. With this, I conclude, and I thank the organizers for all their hard work to put these things together.